Alright class, we are heading into chapter 5. Alright, I am going to grade your final or your first semester finals this weekend here. But we are going to jump into chapter 5. And chapter 5 is all about identities. Just real quick here before we get going, just want to get you the rundown where we're going with this here. Identities. Alright, what do we need identities for is to get to chapter 6. And so identities, I know you've done this before. I think we did it in chapter 1, particularly chapter 1.4. We were introduced to identities and how to prove that the right side and the left side are the same. Well, we're going to jump way in depth into this. We're going to spend a whole chapter just doing identities. And the whole point is to get us to chapter 6, which is to solve equations. Now in algebra, we know what that means, right? You guys have been solving equations ever since algebra 1. We're going to start solving trigonometric equations here, but in order for us to do that very well, we need chapter 5. We need to learn all the identities and all the little tricks of all the identities here. So let's start off. Let's go for it here. So chapter 5, identities and formulas. That's what we're going to learn. And chapter 5.1, let's kind of reintroduce ourselves to what we learned in chapter 1 about identities, and we're going to go just a little bit more complex with it here. But 3 things we're going to do in this chapter. Here it is. This you have done before. Prove an equation as identity. You're going to prove that the right side and the left side are equal to each other. This one I don't think we've done, so give a counter example. If you know it's not an identity, can you give an example that proves it to be not an identity? And then the third part here is we're going to jump with our calculators. So if you don't have them out, you might as well take them out. The third part is to use our graphing calculators to even figure out if it's identity or not, and then we'll go from there. So with that said, let's jump to review our basic identities. This is from chapter 1, and we've been working with this all semester long, so we know what this is. So do you remember the reciprocal identities? Cosecant is the reciprocal of sine and its equivalent. Secant is the reciprocal of cosine and its equivalent. Now don't write these down. You don't have to write all these identities. You know them. They're in your textbook. We're just kind of a quick reminder of all these. Alright, cotangent and tangent are reciprocal of each other. And then also the ratio identities. We've been using this a lot. This should be ingrained into you by now. Tangent is sine over cosine. If you're looking at cotangent, cotangent is cosine over sine. So notice cotangent can go two different ways here. Cotangent can go to a tangent relationship, or it can go to a cosine-sine relationship. So just depending on what we need to be doing, we're going to choose which one we want to go with. Alright, and then the Pythagorean theorem identities of sine and cosine. Seen those before. Alright, and then all the equivalent ways we can write it. So 1, 2, 3, 4. You can write the sine squared theta plus cosine squared theta equals 1. You can write it a whole bunch of different ways. Or cosine squared theta plus sine squared theta equals 1. It can be written numerous ways. And the other Pythagorean theorem identities, we've been learning those too, these guys here. So the relationship of tangent and secant, the relationship of cotangent and cosecant. There's a Pythagorean theorem relationship there. Alright, you guys have known these, seen these before. Let's jam. Let's do an easy one here, just for starters though. So, is it true? Can you prove that secant theta multiplied by cotangent theta is equal to cosecant theta? So from chapter 1, this is in fact really similar to what we've done in chapter 1 here. I'm going to prove this. Okay, I'm going to prove it by showing that the right side and the left side are the same to each other. Or they're the same thing. And so we learned in chapter 1 the easiest way to do it is just to convert things into sines and cosines, since those are kind of like our basic forms. So secant is 1 over cosine. Cotangent, so here it is. Do you want to change it to tangent? Or you want to change it to a relationship between cosine and sine? And I'm thinking in this case, I'm going to go with relationship of cosine and sine. There it is. And then on this side, we normally, again, we like to write things in terms of sines and cosines. Sines and cosines. So cosecant is 1 over sine. Perfecto. All right, we look back at this here, and we're just going to keep on going. So I'm going to cancel off the cosines because they're going to reduce each other, and I got myself 1 over sine theta is equal to 1 over sine theta. Perfect. I am done. So the way math books indicate they are done, they have this little check mark sometimes. Other math books, yours included, they have this little box. Yours is like a purple box filled in saying, hey, I'm done. Okay. The math books, up until about 1970, they used to have this. In fact, my old trigonometry book actually had QED. QED whenever they solved a trigonometry identity. There it is. So you're saying, what is QED? I know, it's kind of weird. How about this? I'll just let you guys, if you're bored out of your mind this weekend, look up QED. We stopped using it. I'll give you a hint. We stopped using QED when we stopped teaching Latin in the schools. I'll just stop there. I'll let you guys figure that one out. Okay, so on Monday, come and tell me if you found out what in the world is QED. All right, on to number 2. Again, kind of like a practice run. Kind of easy. I think this still should be a pretty easy one here to do. Write it out first. Go for it. If you can stay ahead of me, that's even better. All right, one thing that we don't want to do, and this has come up in class as well, is you don't ever want to move across the equal sign. You're not moving from the right side to the left side. You can't multiply both sides by sine or cosine because we are not solving an equation. We only move things around whenever we're solving an equation. That's going to be chapter 6. All right, chapter 5 is going to be right side equals left side. Let me tell you how, or let me show you how. All right, as I'm looking at example number 2, I notice that I have a sine on the right hand side by itself, has a little 1 next to it, so I'm thinking I'm going to convert everything into sines and cosines. So tangent is going to be sine x over cosine x. Cosine is just cosine. Cotangent is going to be, I think it's going to be cosine over sine. I think that's the equivalent form. And notice this side is going to be exactly the same. Now, do you need to write it down each time? You don't have to. I like to, because then I kind of think about where I'm going. That's all. All right, we have a choice here. You can either solve the inside here. You can start simplifying the inside as if you want to. That's perfectly fine to do. Or you can distribute this little piece right over here. So you know I'm going to distribute this little piece, and then I'll see if I need to do anything here. All right, so let me distribute this side. So going to the first one here, this becomes sine of x, cosine of x divided by cosine of x. Perfect. Okay. Multiplying into the second fraction, this gets me sine of x multiplied by cosine of x. That's this times this on top. And then I have cosine x and then the sine x that was originally on the bottom. All right. And, okay, so I won't write it down over here. If I'm simplifying, if I was simplifying, then yes, I would. But since this is just going to stay the same. Oh, you know what I do see? I do see a lot of things crossing out here. So there's sine. Oh, this is easy. I like this way bunch now. Cosines are gone, sine is gone, and I'm left with a 1, which now I do want to write it down. This one, because in the last step, you want to write down the fact that the left side equals the right side exactly perfectly. All right, and I'm going to use the box, just like your book uses the box. There's my little box to say I'm done. Okay, are we good? Well, you can't really answer that because it's a recording, so I'm not really asking you. Never mind. All right, this is the way the book looks at it and kind of gives you the guidelines. So it says, look, you want to start off working out the complicated side first. You want to look for substitutions you can make to simplify things for you. Think about adding fractions. Think about distributive property. Think about all the things you normally do in order to simplify expressions. Okay. Change things into sines and cosines, and if you can do that, that would help a lot as well. And then this is kind of a good one. You always keep on what you're trying to get to, right? Remember, you want to keep on figuring out, okay, this is going to make it this way. So you kind of work towards the direction you want to go to. All right. And I kind of just simplified it a little bit here. So convert things into sines and cosines. Work on both sides to simplify them as much as possible. And one more little thing that the book did not mention. I'll mention it to you. You'd be like, free, totally free here, is use conjugates. You want to use conjugates sometimes. So what's a conjugate? Sometimes you want to multiply both top and bottom by 1 plus 1 by sine theta. Or you might need to see the need that you have to multiply both sides, both top and bottom, by 1 minus cosine x. So we'll see if we get to any one of those. Alright, so there it is. So now let's get complicated a little bit more. All yours. Try it first. Go for it. Alright, so I'm going to go with it here. So cosine. If we can, yeah, let's do that. Let's get this guy to a cosine x over sine x minus 1. That's going to be that position there. This one is a fun little position. We can either distribute, or we can change everything into sines and cosine. Let's do that. Let's go with changing things into sines and cosine. Let's see if we can see more things more clearly. So cosecant. Cosecant is 1 over sine. Secant is 1 over cosine. And I think we have something like the same thing that we just did with okay, I'm writing down, it's a habit now, I'm writing down each of the pieces even though they're exactly the same. But here it is. You can either simplify the stuff inside the parenthesis, which I do not suggest. I suggest distributing here because it might work out a little faster. So distributing this little cosine x on top gives us cosine x over sine x. Minus sign comes down. And then let's multiply this guy in. So this is going to be, let's see, cosine x on top. Oh yeah, cosine x on the bottom. And hopefully you guys already solved it. And then again, want to rewrite it so that it looks exactly the same. This is going to be, yep, let's keep that one exactly the same still. And this turns into a 1. So dun da da da, I'm done. There's my box. Next we're going to start proving this. 1 over cosecant x minus cotangent x is equal to cosecant x plus cotangent x. So we have fractions on our hands here, so we're going to try to see how we can simplify that. So let's go for it as we've done before. Let's take the time to change everything into sines and cosine. So this is going to be, let's see, cosecant is 1 over sine of x minus sine. And this would be cosine of x over sine of x is equal to, let's see, cosecant will be 1 over sine of x plus cotangent again is cosine over sine. So in this case, what I think I'm going to do, I think I'm going to just simplify the right hand side first, and that seems to be easiest. They already have common denominators. So it's going to be 1 plus cosine of x here over sine of x. And that is pretty simple. I think that's kind of done right there. Alright, so the whole course of action here is to look at the left side, keep on simplifying it until we get what it looks like on the right hand side. So first things first, I'm going to keep the 1 as is. And these guys both have a common denominator of sine. So I'm going to put this together as 1 minus cosine of x over sine of x. Alright, is that good? Alright, and then I'm going to say, look, this is just a reciprocal, isn't it? It's 1 over something. So reciprocal puts it like this. So we have ourselves now sine of x. I'm just going to flip this upside down, put it on top. Alright, so this is what I have now. I got this is equal to this. That does not look right. Notice we have a plus cosine on top, we have a sine on the bottom, and that's just, and everything is simplified. Everything is so how do we simplify this some more? Because everything is down to cosines and sines, and there's nothing I can do to simplify anymore. At least maybe not yet. I'm running out of room here, so let me rewrite the problem on the next slide. So I have sine of x over 1 minus cosine x equal to 1 plus cosine of x over sine of x. Okay, so the only thing that we could do, let me actually even change pin color here just so we see it. We are going to multiply by the conjugate. This is what we're doing here. Multiply by the conjugate. I'm going to multiply one side. Doesn't even matter which side you want to go with. It don't matter. I'm going to multiply one side by the conjugate of this one right here. The conjugate of 1 minus cosine of x is 1 plus cosine of x. Alright, this is the trick of the trade. Ready? That. And I'm going to have to multiply the bottom as well. So notice I'm not moving things across the equal sign. The equal sign is still the same. It's still right side and left side. And so with that, these two get multiplied together. I'm going to keep them separate. So this is 1 plus cosine of x multiplied by sine of x. On the bottom, here's what we're going to be doing. We're going to be multiplying this out. One plus cosine of x multiplied by 1 minus cosine of x. If you go back to your algebra days, do you guys remember when you multiplied something like this? X plus 3, x minus 3. Do you remember when the signs in the middle were different? What happened was the middles canceled each other out, right? So when you went like this, you got your x squared, you got your minus 3, you got your plus 3, and then you got your minus 9, and what happened was these middle terms canceled. So you said, oh, you know what, you didn't need to do all that work. You could have just multiplied your first ones and your last ones, and you would have got this already. Well, same thing's going to happen here. We're going to multiply our first one, which is 1 times 1, and then we're going to multiply our last ones, which is a positive cosine minus a negative cosine makes negative cosine squared x. And then we have ourselves an identity. It's the Pythagorean theorem identity. If we know this to be true, sine squared theta plus cosine squared theta is equal to 1. We also know that this is true. And that's the one that we want. We want an equivalent form of our Pythagorean theorem identity. And if that's the case, this whole piece here is going to change for us. So the top stays the same. Let me move it over here just so we can see things. So the top stays the same. It's 1 plus cosine of x. Sorry, my pen keeps on doing some funky stuff here. Times sine of x over, so here it is. So instead of writing 1 minus cosine squared x, we are going to write the equivalent form of sine squared x. And then we should see what's going to happen now. We should see the fact that that sign is going to disappear completely, and this one's just going to go down to by 1. So I got myself 1 plus cosine x over sine of x, which is the same thing as the right hand side now, and love it. There it is. I have proved. get my little square over here. I've proved that those are exactly the same, but I proved it by this little extra little trick. The trick is to multiply by the conjugate. Yay! All right. One more we got to think about is this one right here. If you change everything into sines and cosines, you can still do this one this way. It just takes a little bit more effort. But notice on this problem, notice you have no sine or cosine or anything else besides secant and tangent. And so what should pop into your mind is this little relationship from your Pythagorean theorem. So another one, if you see an equation that only has cotangent and only has cosecant, you may want to use those identities. Alright, so let's see how this is going to work out. Alright, so again, can you change everything into sines and cosines and work from there? Absolutely. It'll just take you a lot longer. So here's what I'm going to do. I'm going to say to myself, I'm going to try to substitute things. How about if I do this here? If I see secant squared, I'm going to change it into 1 plus tangent squared theta. That's it. That's what I'm going to do. So there it is. I see a secant squared. I change that into 1 plus tangent squared theta. So there it is, and hopefully you see what's happening here. Like, oh, okay, I changed it. The tangent squared thetas disappear, or x's disappear, and I am done. There it is. There's my little box. I've just proved the right side and left side are the same, and I'm done. So notice those Pythagorean theorems involving tangent and secant and cotangent, cosecant help to go this a lot faster sometimes. Alright, now we're going to do the exact opposite. We're going to have to show that the right side and the left side don't equal to each other. We have to show that this is not an identity. And the fun thing is, when you show something is not, you just have to figure out one time that it does not make sense. So for this one, we want to show just a counterexample. So we're trying to show that this is not an identity, and it only takes one time. And so here it is. We're going to prove this not to be an identity. Cool. Alright, now we know, well, let me change pin color just real quick here. We know that this is an identity. If it's sine squared theta plus cosine squared, that is an identity. That is totally true. That's a Pythagorean theorem identity, right? But if you take off the squares and you just say, oh, just sine plus cosine does not equal 1. Okay, how do we prove it? We have to let x be something that will disprove the case. That's it. That's all. And your book uses radian measurement, so I'm going to use radian measurement as well. So pick something, show that the right side and left side don't equal to each other. Now, sometimes that you may pick something that actually they do. So just like as soon as you do that, like erase it and pick another degree, angle, or radian measurement here. So I'm going to pick pi over, I don't know, 6. So I'm going to let that be true. Put pi over 6 here. Put a pi over 6 here. And then what they do is they put like a little question mark on top of the equal sign. Like, will it be true? I'm not sure. Total mystery. Let's check it out. So sine of pi over 6. What is the sine of pi over 6? It is 1/2. Oh, 1/2. Cosine of pi over 6 is root 3 over 2. And the question mark still remains. And as you do this here, you put it in and just simplify the process here. And right over here, when you're saying, hey, this is the last step, what you're going to do is you're going to put a slash through the equal sign. And you're going to say, see, told you it wasn't true. And then you're done. So again, a little box to say I am complete with my assignment for this problem. Okay, so that's proving something is not an identity. You just have to prove that in one simple case, it's not an identity. Alright, prove that sine of x is not equal to cosine of x. Prove that that is not an identity. So I just want to show you, just rule something here that. So I'm going to prove this is not true. And you should know, think about it in your mind, when is it true that sine of x does equal cosine of x? Is that ever a time that it's true? So this is something that you may get stuck on the homework. You may do it. So if you said, oh, you know what, I'm going to let x is equal to pi over 4. So notice if you do this, you're going to put it in question mark. And then this guy is going to be root 2 over 2. And then all of a sudden this guy seems to be root 2 over 2. And you're like, oh shucks, I don't want that. So it's just that time that these are true, but they're not true all the time. So the way we should do this is like this. You're going to set up the problem. You're going to disprove this case. And again, you're just going to have to set something that's going to not be true. So I'm going to use my pi over 6 again, since we did it for the last problem. There it is. Sine of pi over 6. Question, is it true? I'm not sure. Let's see. Total mystery. Let's see. Okay, sine of pi over 6 is 1/2. And cosine of pi over 6 is root 3 over 2. And I'm going to slash that equal sign saying it is not true. Alright, with that problem is done. Put our little box and done. Alright, and now we move on to the last and final part of 5.3. It is using your graphing calculator, you're going to decide whether an equation is identity or not. So if it is an identity, you're going to do what we did before in the first part of this section. If it is not an identity, you're going to give a counter example, just like we did in the second part. Alright. So here it is. I just went and I did the same one that we did in example 7 here. So use your graphing calculator, determine if it's an identity or not by graphing the right side and the left side. If it's so, then you have to verify it, which we know it's not an identity already. But if it is not, then you have to prove a counter example, which we already proved in example 7. So it's really just a matter of using the calculator right here. So we are going to graph sine x on one side, or maybe like y1. Cosine is y2. Before we get there, just kind of think to yourself here, this is a sine function. You guys know how to graph sine functions, right? So the maximum is going to be 1, minimum is going to be -1, has a period of 2 pi. So you just want to give at least a good enough of a graph for it to see. Same thing for cosine. Max 1, minimum -1, goes out to 2 pi. So with that, let's get your calculator. If you haven't got it yet, turn it on. And here's, I got mine. I got my TI-83 Plus here. And I'm going to go for it here. So, turn it on here. So the first thing we got to do is still check our mode. Make sure our mode, and make sure we are in radian mode, because that's the way we want to do this here. So radian mode is checked off for mode. Perfecto. Okay, and then we want to go to our window. So we have x min, x max. What we want to do is want to go from -2 pi to a +2 pi. So we just want to make sure that is situated here. So your pi button, don't forget your pi button. Some calculators have it differently, but the pi button for 83 is above the exponent or the caret key. So you have to click on second and then this function here to get you 2 pi. Then talk about the x scale. This is where you have those little tick marks. So if I'm going from -2 pi to +2 pi, I'm going to just make my tick marks to be pi over 4. Pi over 4. So again, going to that pi key again. divided by 4 would give me what I want. Alright, and then remember, maximum, minimum is positive 1, negative 1, so I'm going to leave a little bit of space. So how about a negative 2 to a positive 2, and then we go from there. And the x scale is going to be a 1. Let's go for it here. Let's look at our graph before. Ooh, that looks a little off. I think my y value is too high. Yep, it is. Real quick here, let's go back down. Get a 2 in there instead of a 3. Okay, now this is the way I want to see it. Perfect. Okay. And then remember our window, and let's talk about this again here. Notice our x scale is by 0.4, so that's pi over 4. So that's going to be a pi over 2. That's going to be a 3 pi over 4. That's pi. This is going to be 5 pi over 4. We call it 6 pi over 4, 7 pi over 4, 8 pi over 4. So we got what I wanted. Now let's put in sine of x. And close off the parenthesis after you put in your variable. Click enter, put cosine of x. Alright, and give you a little time to do that here. And we are ready. We're ready to graph this. So if we see just one exact graph that's graphed, that means this is an identity. If we see two different graphs being graphed, that means we see this is not an identity. So let's go for it. So this is sine of x right here. Sine of x, recognizable. Then we have cosine of x. Yes, that is true. Look at that. Those are not the same graphs. They're off. Oh, in fact, you know what? Remember how we did pi over 4? Remember how it actually was the same? That's why right there, because it's the same on that interval only. Then it's off afterwards. So we put in pi over 4, pi over 6, then it became off. So sometimes the counterexamples may not work as well. Alright, the next one. So use your graphing calculator to determine if its equation appears to be an identity or not. If it is, verify it. If it's not, prove or provide a counterexample. Now this one we already proved. This is example 1. I just want to show it to you via calculator here. So the only little problem we have with our calculators is it does not put in secant, cotangent, and cosecant, all the ones that are listed here. So before you put this into a calculator, you got to change it into either a sine, cosine, or tangent. So this one's going to be changed into a cosine of x. Let's put a little parentheses around it. We're going to multiply it by cotangent. Cotangent is cosine over, I'm going to get to that in just a bit here, over sine. Alright, so that's what we're going to really plug into the calculator. This is 1 over sine. Okay. The funny thing is, what you saw before, when you plug into a calculator, like when you put in sine, all of a sudden it opens up a parenthesis like this. Then you plug it in, and then to close off the parenthesis, you got to put in the back parenthesis. So let me show you how I would plug this into the calculator. I'll probably start off with, actually it has to go like this, right? It has to have these little extra parentheses around the cosine, extra parentheses, sine, and cosine here. So the way you plug it in probably would be open up a parenthesis to do this part here. So you could put 1 divided by, then we're going to plug in cosine. Once you plug in cosine, you're going to have this little open parenthesis. Then you're going to close off the parenthesis for the cosine. You're going to close off for that first term there. You're going to multiply now. Alright, this is even more fun. Here it is. This would be cosine. So open up another parenthesis, cosine, close off the cosine, then divide it by, open up sine, opens up another parenthesis, get an x in there, close off the sine, then close off the second term. Okay, that's the way you would do that. When you plug this into the calculator, you really don't need a parenthesis around the 1. You're just going to plug it in as this. That'll be a lot simpler version. It's open up a parenthesis, you're going to put an x, and you're going to close off that parenthesis at that point. So here's the two things we're going to plug in: this one and that one to verify if this is an identity. We already know it's an identity because we did it in example 1. Let's go for it then. Alright, I cleared my plots here. If you haven't, then just kind of click on it and then click on clear. But here it is. So 1 minus cosine, put the x, close off the parenthesis for cosine, and then close off the parenthesis for the first term. Put a little multiplication bar, that's what I like because it really keeps them separate in my mind. Open up a parenthesis, on top we have cosine, put an x, close off the parenthesis for cosine, divide by sine of x, close off the parenthesis for sine, then close off the parenthesis for the whole term. Okay, that's the first term, or the left side. Okay, the right side is 1 over sine. Make the x, close off the parenthesis. I think we're ready for graphing. Let's check this out. Let's see how this graphs. So here it is. Here's our first term. This is y1. Notice it's coming across, coming across, coming across. That's fine. That looks like pretty good stuff here. And then it stops. And then you assume as it's coming across, it's building another parenthesis, building another function. This is y2, but notice nothing's happening. There's no new one here. So that means you know that those are the same exact graphs as illustrated also in example 1 anyways. Alright, so hopefully that again I gave you an idea of what to look for in the graph. Alright, there's one particular, and we'll finish off with this one, there's one particular thing you should know, should see, should understand, that this is not an identity. So please show that sine of a plus b equal to the sine of a plus the sine of b is not an identity. We're going to show that. So give me a counter example that makes that true. Alright, the only little problem is with this is, let's kind of think about this in terms of degrees here. If I say I'm going to use 30 degrees for A, and I'm going to use 45 degrees for B. The only problem is when you add these together, for the left side you're going to get 75 degrees, and we don't know the sine of 75 degrees. So it has to be two things that we know angles of. When you add them together, we will know that angle as well. So hopefully you thought about it. Think about it for a little bit here. Shout it out. Well, no, don't shout it out. Just a little bit here. Think about it here. So yes, if anybody said this, A for 30 and B for 60 would work just great, because A plus B would be 90 degrees. There's your one. Okay, and the book wants you to do it in terms of radian measurements. So this would be, this would be pi over 6. This would be pi over 3. And this would be pi over 2. Let's make sure that works. Is that true? Pi over 6 plus pi over 3 would make pi over 2. So pi over 6 plus pi over 3, does that actually give me pi over 2? Now let's see, I guess we need common denominators, which would be 6. That needs a multiplier of 2, therefore that gets a multiplier of 2, so 2 pi. And adding the tops together, leaving the denominator the same, adding the tops together gets me 3 pi over 6, which gets me pi over 2. That is perfect. Okay, just verified that is true. Okay, now let's go with our example here. So sine of A plus B, we're trying to disprove this, and we're going to use a counter example by let A equals pi over 6 and B equal pi over 3. Let's do it. So sine of pi over 6 plus pi over 3, we don't know if it does or not, we'll see, of sine of pi over 6 plus sine of pi over 3. Okay, so we know, based upon this, we know that pi over 6 plus pi over 3 makes pi over 2. Cool. So we got sine of pi over 2. Don't know yet. Plus sine of pi over 3. So now let's go with it here. So sine of pi over 6, or sorry, sine of pi over 2 is 1. Don't know yet. Sine of pi over 6 is 1/2. The sine of pi over 3 is root 3 over 2, and that is not going to be the case. That's 2 over 1 plus radical 3, and we put a slash through it. So what do we know? That this is not the case. So we know that the sine, notice what we know, the sine function doesn't distribute into here. It doesn't do that. Not in trigonometry. Alright, so we'll stop with that.